So today's class is the topic differentiability. So definition of differentiability is a function f is said to have a derivative at any point x if and only if it is defined in some neighborhood of the point x and limit h tends to 0 f of x plus h minus fx by h exist finitely. That means a function is said to be differentiable at any point x if this quantity exists finitely. So now the relationship between differentiability and continuity. It's a very important topic. So now the theorem. If a function is differentiable at any point, it is necessarily continuous at that point. That means differentiability implies continuity. Sure. So now proof of this theorem. So in your theorem, if a function f is differentiable at any point, that means you should consider that the function f is differentiable at any point. So let f be differentiable at x equal to c. Then obviously by the definition, see this definition, this quantity, that means limit h tends to 0 f of c plus h minus fc by h exists finitely. Sure. And this, consider this quantity is equal to f dash of c. That means f dash c equals to limit h tends to 0 f of c plus h minus fc by h. Sure. Now calculate f of c plus h minus fc. So now there is an adjustment. That means f of c plus h minus fc by h into h. Got it? Now taking limit as h tends to 0 on both sides. So limit h tends to 0 f of c plus h minus fc, that is equal to limit h tends to 0 f of c plus h minus fc by h into limit h tends to 0 h. That means limit of this part into limit of that part. Got it? So now look at that. Separate the limit. So limit h tends to 0 f of c plus h minus limit h tends to 0 fc, and that should be, this one is the nothing but f dash of c. That means derivative at the point, derivative of the function f at the point x equal to c, and this limit h tends to 0 h, that should be 0, and the total quantity should be 0. So now let's look at that. Limit h tends to 0 f of c plus h minus limit h tends to 0 fc, that should be 0. This means, look at that, this quantity is independent of h. So this is a constant, and that is fc. So this value, that means limit h tends to 0 f of c plus h minus fc, limit h tends to 0 f of c plus h is equal to fc, and this shows that it is continuous at the point x equal to c. Hence by the definition of continuity, f is continuous at x equal to c. Now remark of the previous theorem, that means continuity may not implies differentiability. How to show it? For example, consider the function f x equal to mod x for all x belongs to R. That means domain is your R. So now clearly if 0 equal to obviously mod 0, that is equal to 0, and limit h tends to 0 plus, that means right hand limit of x, that should be, since if x greater than 0 mod x equal to x, so that should be x, and that should be 0, and limit x tends to 0 minus fx, and that should be minus x, and that should be also 0. So clearly left hand limit equal to right hand limit equal to function value at the point 0. Hence if it's continuous at x equal to 0. So now for the differentiability, so calculate the left hand derivative at x equal to 0. That means limit h tends to 0 minus f of 0 plus h minus f0 by h. Sure. So now look at that. 0 plus h means fh, and now h tends to 0 means h is less than 0. So since x is less than 0, mod x should be minus x. So this should be minus of h. And clearly f0 equal to obviously 0. So minus h by h, that should be minus 1. So left hand derivative is minus 1 at the point x equal to 0. So now right hand limit of f at x equal to 0. That should be limit h tends to 0 plus f of 0 plus h minus f0 by h. And look at that, f of 0 plus h means fh. And since h tends to 0, h is positive. So mod x should be x. So fh should be h. So this should be h. Minus f0 is obviously 0. So h by h means 1. So right hand limit should be 1 at the point x equal to 0. So left hand limit not equal to right hand limit. And hence if it's not differentiable at x equal to 0. So now the corollary of the above theorem. So every differentiable function is continuous. That means if a function is differentiable at any point on its domain, then this should be continuous at that point. So problem number 1. If f is differentiable at x equal to a, find limit x tends to a, x fa minus a fx by x minus a. Sure. So now in your question it is given that if it is differentiable at x equal to a, then obviously this limit, that means if dash of a, that is equal to limit x tends to a fx minus fa by x minus a exists finitely. Obviously it is by definition of derivative. So now we have to find it, this one, write this one. So now this is the adjustment part, afa minus, sorry, plus afa. It is the adjustment part. Look at that, xfa is here. Adjustment is minus afa and plus afa. And this should be your minus afx. So from this two, common fa. So x minus a into fa minus, and from that two, common minus of a. That means minus a into fx minus fa. Sure. So now separate it. So this should be limit x tends to a, x minus a into fa by x minus a, minus a into limit x tends to a, fx minus fa by x minus a. And that should be that x minus a cancel out, and that should be fa. And I think this one is there, f dash of a. So put it f dash of a. So now it is your answer, that is fa minus a f dash of a. So now the problem number 2. Examine the function f for continuity and derivability at x equal to 0, where fx equal to 1 minus x square if x less or equal to 0 and 1 plus x square if x greater than 0. How to solve it? So first of all, the continuity. First part is the continuity part. So clearly if 0 equal to, say this x less or equal to 0 is x equal to 0 is here. So if 0 should be 1 minus 0 square, and that should be 1. Now limit x tends to 0 minus fx, that means left hand limit, and that should be limit x tends to 0 minus 1 minus x square. So put x equal to 0 here, so 1 minus 0 square equal to 1. So now left hand limit x equal to 0 is fx equal it should be 1. Got it? So right hand limit equal to left hand limit equal to function value. So if it's continuous at x equal to 0, clearly. So now for the differentiability part, so left dash of 0, that is equal to limit h tends to 0 minus f of 0 plus h minus f0 by h. So limit h tends to 0 minus fh minus f0 by h. 0 minus means less than 0. See this example function. If x less than 0, then fx equals to 1 minus x square. So since h tends to 0 minus, that means h is less than 0. So fs should be 1 minus h square. So put it 1 minus h square, and f0 should be 1. So this one cancel out. So minus h square by h, and that should be 0. Sure. So now for the right hand derivative part, r f dash of 0, that should be limit h tends to 0 plus f of 0 plus h minus f0 by h. That should be f of h minus f0 by h. So since h tends to 0 plus, that means h is greater than 0. So see this example, function fx equal to 1 plus x square if x greater than 0. Since here h is 0 plus, that means h is greater than 0. So fx should be 1 plus h square. And if 0 is 1, so 1 cancel out. So h square by h, and that should be 0 obviously. Sure. So left hand derivative equal to right hand limit derivative at that point x equal to 0. Hence f is derivable at x equal to 0. Thank you so much.